Henry, you get barely any fuse, so run. Please, please, please. My name is Het Sathasia.
I'm Henry Spicer.
I am a first-year UC Davis student going into my second year.
I'm just graduated high school and I'm going to Berkeley in my first year very soon.
And this is our summer 2024 project.
So basically, this last summer we started and failed building a rocket motor, and this year we wanted redemption. And we wanted to build one that was not just really powerful, but also one that we could fit in a rocket and actually launch it somewhere.
Mm-hmm. Step one was to recreate our results from last year, or at least improve on that. So we recreated our KNSB fuel. We made 3 iterations of that. KNSB stands for potassium nitrate and sorbitol. We mixed those together in an electric skillet to prevent sparks from forming and it auto-combusting in the pan itself.
Yeah, so basically you mix potassium nitrate and basically what is powdered sugar, and you mix it until it melts and you pour it into a casing like a PVC pipe, which is what we did here. One thing that we learned was before we did this, we were packing fuel in when it was in its solid form, so as a powder, and we learned that it took a really long time to burn that way, meaning that there was less thrust but a lot of flame, and that's not really helpful when you want to get off the ground.
Yeah. We made an end burner grain, and also the PVC started to melt, which is less than ideal.
Oh yeah, it deformed and everything. And we eventually got it to work by melting it down and putting a rod in the middle of it, so like this rod.
Similar to this one.
So the reason why you want a rod through the whole thing is because it allows it to burn quicker, because there's more access to the exhaust pipe or our nozzle, and that makes us be able to have more thrust. So when you're pouring it, because it's basically like a liquid, or it's
slurry.
more like it's like a slurry sludge type thing, and yeah, that's really important when you're pouring it. You have some rod in there, so you have that access hole. But then we didn't have any way to measure the thrust, and if you have no way to measure the thrust, then there's really no point in having a motor. Yeah. So we built this. It looks a little dirty because it's very well used. We call it our thrust stand. Do you want to go into explaining?
Yeah, so we use a load cell, which is a piece of metal that has 3 strain gauges attached to it to form a, can't remember the exact term, but it's a bridge. And we use that to measure the bend in them because their resistance changes as they flex. And we have an amplifier right here, which then plugs into our Pico, and we can then measure the thrust, similar to how a scale or other weight measuring devices work.
Yeah, so basically you put the motor in here, you light the motor, and as you can kind of guess, this thing bends like that, and we measure that thrust there, and we convert it into kilograms in milliseconds time. So we get about 80 messages per second over the new load data, and we can plot it on Google Sheets or something and figure out our total force.
Our total impulse and specific impulse.
Yeah, so we use, for every single project that involves electronics here, we use a Raspberry Pi Pico, and we use that because it's very light, it's very small, but it's able to do not only computation, but logging, as an Arduino can't really do that, and it's also quite powerful for the amount of power it draws. So we can do stuff like shove it in a rocket and stuff like that. And another problem we had was we didn't want to use, fuse was a little scary because you had to make a really long fuse. You lit it and then you basically ran away. But fuse is kind of scary to use, and it's also boring. So we threw that away and we made, what do we want to call these?
Igniters.
Igniters. We made igniters. So it also has a Raspberry Pi Pico, and it just uses big batteries to light a E-match, which basically takes a bunch of voltage and it basically makes a big spark, which ignites your motor. So it's actually wireless, and we tested it probably 30 feet away, and it worked pretty well. So yeah, there's a safety switch, and we have these cool like nuclear launch switches, yada yada. But yeah, you can switch the E-match whenever you want, and it's been quite nice, and we haven't even had to recharge the batteries yet.
Yeah.
And after we got done with this part of the project, we didn't like how much thrust we were getting with our sugar motors.
Yeah.
So we looked into this new formula called APCP,
which stands for ammonium perchlorate composite propellant. It's similar to what the space shuttle engines used. We just made a simpler version. So it's gray. We poured it into these red cardboard tubes just because it's not hot. It doesn't melt. Instead, you have to, it's a pretty intensive mixing process. You need a vacuum chamber. You need to wear a lot of PPE, like a respirator. Do you want to?
Yeah, so when the difference with this fuel is, like Het said, you don't really melt it in. It's more like a packing thing. It's more like a Play-Doh. So you basically mix ammonium perchlorate, aluminum powder, and this resin that binds it, and it cures for 48 hours. And when making it, it's very important that you know that it's really bad hazard. There's the fumes that come from the resin's super dangerous, so you have to wear respirators and gloves and safety glasses, because if it gets in your lungs or inside your body, it's really bad for you. But this propellant is really, really, really powerful.
Yeah.
Do you want to go into
those numbers?
Yeah.
So this, well, first we tried using an aluminum nozzle. So we made a convergent divergent nozzle using the open motor simulator. The first issue with that was we accidentally doubled the motor.
When we made it in CAD, we doubled the size, so it looks pretty cool. But the chamber, what we observed was when we lit the motor, a big part of when you light a rocket motor is the chamber pressure. And what was happening was the chamber pressure was building and then dropped. So the motor thrust was like going on and off. It was like toggling. Yeah, it spiked, drop, spike, drop, spike, drop. And we wondered if it was our fuel problem. And then we checked in CAD and we realized that this was the wrong size. And once we got our new one, we put it on, and this one's exactly half the size. Once we put it on, it worked, but it exploded the nozzle.
Yeah,
or
it just melted a hole straight through.
It just completely got red hot and melted downwards. So our next solution was using steel. The problem was with steel, if you wanted it to get machined, it would cost hundreds and hundreds of dollars, which we didn't want to spend. So we found a manufacturer in China that would 3D print it for us out of metal, and that's worked really well for us.
Yeah.
It's just really, really heavy.
It's heavy and it rusts super easily due to the increased surface area. But other than that, works beautifully.
And these nozzles, they are held in a aluminum shell that we made. And if you want to go into the stack up.
So we first have an internal retaining ring on the bottom. We then have what we call the back cap. It's effectively a nozzle, but without any of the holes through it. Just a single O-ring and a small stud coming out. And then we have the cardboard tube, which goes roughly in the middle. That's just to insulate the aluminum from the fuel itself, because the fuel itself gets incredibly hot, upwards of 1,000 degrees Fahrenheit, and the aluminum melts at a relatively low temperature versus that. So yeah, cardboard acts as a great insulator.
Yeah, the cardboard is like an insulator for the aluminum. It protects it just long enough for it not to melt or bend.
And then the nozzle goes on.
So just for reference, this is an O-ring. It's just this silicone ring that you slide. Here, I'll show you on this. Oh, here, actually there's one on this. So you slide over it, and when you press it into the aluminum and it creates a vacuum. It's just like electricity. Air likes to find the quickest and easiest way out of things. And when you build up a super, super high chamber pressure inside the nozzle, it might find its way around the cardboard and out the back, or around the nozzle. But that means your motor is gonna has less performance. So with these rings, it maintains the vacuum inside.
Oh, the seal.
A vacuum seal is basically what it is. So you get all the power out of the back. But otherwise they don't really hold it in very well. So
Yeah.
we have these snap rings that are super strong that basically hold it in like a clamp. So you put one on one side and one on the other side of the nozzle and the back cap, and as it pushes out, the snap rings hold it in. And yeah, we've had no problem with that at all. So that's how the stack up kind of goes together. And you have to use a lot of grease to get it in, otherwise it kind of tears itself apart.
Yeah, the O-rings really don't like sliding over grooves on the inside of the shaft.
So we figured out that putting silicone grease on the ring and inside the tube really made it easy to slide in. Okay, so now we have our motor, and we have our igniters, and our load cell, and we were able to do a successful test with a steel nozzle, and we figured out that we got a ISP of 225, which is extremely high for our fuel to weight ratio.
Yeah, that's cool.
Okay, so now that we have our motor, and we have, well, I mean, we have all the things that tested the motor, but now we need a rocket to put around this motor. So you want to go into what rocket we chose in mind?
Yeah, so it was a pretty long process to pick the exact rocket we wanted. We wanted something that was pretty light, just because we knew that the motor itself is over 200 grams. We needed something light so that way we could focus on building the rocket. We also wanted it to be simple to construct. A lot of motor construction kits out there require a lot of, like, over 10 hours of work to build it. So we found a pretty low level kit, but we also found something that could fit our motor.
Yeah, and when we got the kit, well, we have our own motor. The kit's designed for a different motor. Our motor's not exactly the same size. Like this was the size of the motor. It doesn't fit. So we had to design virtually every one of the parts that they gave us from scratch, besides for the body tube and the fins.
Yep.
And even then, we still had to cut down the fins. We had to cut down the nose cone. But we designed a new, very, very different way to get it in. It's a 3D printed part instead of gluing in these wooden dowels or wooden rings. And it was just a much better way of getting it in, and it's probably even lighter too. And we glued in the fins, etc. And then we wanted, wait a minute, how are we going to get the parachute out? It's going to fall down to its death. So we designed a circuit using a pico, like always, and a barometric pressure sensor, which is just a fancy word for a pressure sensor. Mm-hmm. So as it gets up really high, the pressure lowers, the atmospheric pressure lowers, and we made a program that figures out when we're at the apogee or the highest point, and when we're falling down. Mm-hmm. And then it deploys a streamer, and the nose cone comes off with a servo that we put inside there. So the servo has a little arm that just, he basically pulled air out of the sensor. The sensor realized that we were really high up, and then once he let go, it dropped hundreds of feet, and the servo released, and it would push off the nose cone. And we use this 18650 battery, which is just a lithium-ion battery that you use in cars all the time.
Cars, laptops,
basically everything.
Yeah.
And so this fits inside the body tube. We also put an air tie inside the body tube for recovery, just in case we have it goes AWOL. But yeah, that's pretty much the rocket. And just a side thing that we did, just for fun, we decided it would be interesting to get an RC car, take out the motor, and strap a rocket engine to the back. So that's what it looks like. We did a launch of it, and the problem, we made a little mistake. We forgot to glue the steering forward, and it kind of turned, jumped up into the air, and started doing really, really crazy circles. But we're gonna do another test of this probably soon. But yeah, so that was what we did over the summer.
Yep. Henry, you get barely any views, so run. Please, please, please.
It exploded, or something happened.
It flew into 100 pieces.
Oh my fucking god.
It's coming down in like 5 pieces.
Here, do you want to get the nose cone?
Yeah. I see it. It's so high. It's so high. Oh my god. And I think I lost it. Oh, I see it. I see it. I see it. No, it's going to their
How
house.
far that way and then came back?
I don't know if we'll find the motor. The motor's gone, but we have data. The data's still here. Yeah.
Yeah.
Wow, that was really good. The nose cone's at that house, but the motor's probably over there. We're just gonna walk over there real quick.
What else?
Oh yeah.
Oh yeah. So the detonators, the wireless connection failed, presumably just because one end of it was in the grass.
Yeah.
If we were holding it up with something, it probably would have worked.
And when it went really high, but then it fell down, and two of the things broke off. Our 3D print broke. The launch lugs seemed to have come off. This was still in. We ripped this out, but
Yeah.
the motor came out. The nose cone came off. What we believe is on accident, and what happened was it flipped over and just started and ripped. And there were so many G's that the epoxy couldn't hold the fins in.
Yeah.
So yeah, it came down and we couldn't find the motor, but hopefully we get some good data off of this guy. So.
Yep. It was still functioning when it landed. So.
Yeah, it was still functioning when it landed, but yeah. I'm very surprised that all these solder joints kept.
Me too.
Yeah.
So after we took it back, we collected the data, but there was a slight issue where the Raspberry Pi Pico only has like a 256 megabyte storage limit, and we somehow left it on for so long that it logged that much data, and when it launched it had no data recording because it was full, which is so sad. But from video we can determine that it did go at least Mach 1, and that was a big goal for us. So, and hey, you want to talk about our next steps?
Yeah, so next summer, at least we're gonna start planning obviously during the course of the year, but next summer the plan is to do liquid or at least do thrust vector control. Simply because attaching more code to things makes it more fun to do. Also, more complexity too.
Yeah. All right.
Yeah, see ya, bye.